Hello all. From the milk you drink to the paper you write on, colloids aren't something that you can avoid. On this realization in mind, let's take the boat to the land of colloids. Without further blabbering, let's hop onto the session. Thomas Graham, a British chemist who is renowned by his pioneering works in the field of dialysis and gas diffusion, was conducting some diffusion experiments through a parchment membrane. This is when he noticed some substances like sugar and salt diffuse readily, while some like jello or gelatin aren't diffusing. On making this observation, he was able to categorize and name those substances into crystalloids for their crystalline nature and non-crystalloids for their amorphous nature. But as an experimental chemist, his curiosity weren't quenched with this. On proceeding with his research, he realized that crystalloid or colloidal behavior depends entirely on conditions. On taking this into account, we can say any substance can be brought to the so-called state of colloidal state by suitable means, and so it will be the part of what we call a colloidal system, also known as colloidal solution or colloidal dispersion. Here, along this short journey, we are about to take a glance at some of the terms and classifications which we will need lately. First of all, let's see the types of solutions. As we know, there are three types of solutions, namely true solution, suspension, and last but not the least, colloidal dispersion. Let's see what a true solution is. A true solution is nothing but a homogeneous mixture of a salt with size less than 10 raised to minus 9 or 1 nanometer dissolved in solvent. In a true solution, we can't isolate the solute from the solution by filter paper, and hence they will not be settling down. We can recognize the true solution by naked eyes if and only if the particles aren't visible. For example, salt and sugar solution. The next kind of solutions is the suspensions. Suspensions are a heterogeneous system containing particles larger than 100 nanometer. Since they settles down with time, it's also filterable in nature. We can identify its particles either by the naked eye or by a microscope. Due to their higher dimensions, they don't give an observable diffusion. We can have the example of a chocolate milk or even a familiar Oreo shake. The third one is obviously the colloidal solution itself. We can define a colloidal system as a heterogeneous system with two phases. That is the dispersed phase, which is the colloidal particles with the size in between 1 to 100 nanometer in diameter, and the second phase is called dispersion phase. It's a solvent or medium in which the above mentioned colloidal particles are dispersed. For example, rice juice, which is technically nothing but starch in water. Now let's learn about the classifications of the colloidal system. Taking nature, the interaction between the phases and the molecules nature, colloids are classified into three as shown. Now let's take a look at each. The first one is the classification based on the states of aggregation of the two phases. Here, based on the three main states of the phases, we have 8 possible permutations. Here, we can see the 8 possible permutations of colloids with the above mentioned classification method. Here, we can see the gas-gas system is excluded since it's a true solution. Now, let's get familiar with another term, the sols. It's a colloidal dispersion in which the dispersed phase is a solid and the dispersion medium is a liquid. For example, gold in water. We can divide the salts into two types, the lyophilic salts and the lyophobic salts. Now, we can take a look at the lyophilic salts. As the name suggests, the affinity between two phases are high, hence they will be much stable. For example, the dispersion of starch in water. These are easy to prepare due to their affinity. More on the preparation will be covered in the next part of the video. Now we have lyophobic salts. As in contrast to the lyophilic salts, the affinity between the phases are very low. Hence, the stability is also low. These are very hard to prepare since shaking or warming the phases are futile. We have the example of gold in water. In this table, we can differentiate the properties of lyophilic and lyophobic salts. The main points to remember are about the viscosity and surface tension, since they play an important role in the identification. The next classification is based on the molecular size and nature. First, we have macromolecular colloids. As the name suggests, the molecules of natural or synthetic polymers possess very high molar masses ranging from thousands to million units. In this kind of colloids, even a single molecule will range in the colloidal particles dimension. The examples are gelatin and rubber. Next, we have multimolecular colloids. They consist of colloidal sized aggregates made from group of atoms or molecules whose size is less than a nanometer. The prominent example is aqueous gold salt. The last one is association colloids. It's interesting since it have a lot in nature to some humans as well. They behave as normal electrolytes in dilute solutions and shows colloidal properties at higher concentrations due to the formation of aggregated particles of colloidal size. The micelles will only form above a minimum critical concentration limit of the substance. Let's see how the micelle formation occurs in the association colloids. For the sake of explanation, let's take the well-known soap case. As we know, we have two parts for a soap's chemical structure. The non-polar hydrocarbon chain represented by the letter R and the sodium oxalate part. At lower solute concentrations, soaps are considerably ionized into RCOO- and Na+. But at higher concentrations, the anions aggregate together to form clusters of colloidal dimensions. The micelle structure will obviously be spherical. As in the figure, the nonpolar hydrophobic tail of each monomer will be directed towards the center while the polar hydrophilic tail faces outside, and the soluted Na+ will be bounded to the aggregates. Thank you all for listening this much.